This is another module where having pen and paper will really help you learn. At any point when we get to a problem, pause the module and try working the problem for yourself. See if you can answer the questions using the formulas we have in this module. So let's go ahead and take a look. We're going to be doing confidence intervals for proportions in this module. Now, the first thing we need to understand about a confidence interval is it has in it a margin of error. A margin of error is something we use in our everyday lives and we might not realize it. So let's think about it. If someone tells you they'll be somewhere between 350 and 410, they've actually told you a margin of error. You'd probably expect them to be there around 4 o'clock. So when we think about it, 4 o'clock is your best guess. And then we have plus or minus 10 minutes. 350 to 410 is a confidence interval with 4 plus or minus 10 minutes. So what do we have here on the slide right here? We have our best estimate is 24% from a sample and a margin of error of plus or minus 3. So let's go ahead and make our confidence interval. If we subtract, we get 21. If we add, we get 27. Our confidence interval right here is 21 to 27. The margin of error is just the plus or minus of it. So remember, the margin of error is just how wide your confidence interval is. Specifically speaking, it is half of the length of a confidence interval. Because this confidence interval, 21 to 27, if we take the length of it, is 6 long. That's because the margin of error is the plus or minus, so it would go up that much and down that much. The margin of error is half the length of the confidence interval. So how do we get this margin of error? Well, we've done a margin of error in the previous module for a standard deviation of the sampling proportion. And when I say we've done a margin of error, we're not using it in the confidence interval sense. We can do it by... So how do we get this margin of error? Well, we are going to use the standard deviation, or in this case, later, we'll use the standard error. A lot of polling agencies use 2 times the margin of error, and we'll talk more on that later. We've seen the standard deviation before for the sampling distribution, but we're not creating a distribution of the sample proportions. We're trying to estimate the true proportion. So how are we going to do this? If we don't know P, we are going to have to use samples. And as it states, the standard deviation of the sampling distribution is not what we're estimating here. We are not doing that. We are going to use samples. So let's use our sample statistic P hat to estimate the true parameter P. Now, what does this all mean? Why are we doing this? This is very important. What we are doing is we're going out to US citizens in one example and asking, are you going to vote for Obama? They probably did this in the 2008 and 2012 elections. What they will obtain is a sample proportion. They want to estimate the true proportion, or the population proportion as it's also known. So think about it. Do they care about what percentage of US citizens say they'll vote for Obama in their sample? To a certain extent they do, but what they're trying to garner from that is, will Obama win the election, which is the true proportion of Americans, or registered voters who do vote, who will vote for Obama. UT could ask many questions of the students. They could ask, are you currently going to football games? And with that in mind, they would get a sample proportion of UT students that say they go to football games, and then they would try to estimate the true proportion of students that go to football games. This would tell them if, student turnout has increased or decreased in recent years, if they have numbers, and they could make an understanding about what they should do and decisions from there. So we're going to call this, since it comes from a sample, a standard error. Now, there's not much to get reversed here. A standard deviation is when we know the truth, when we actually use the true proportion. And that's why we're calling it a standard deviation. Where in this instance, we're calling it a standard error because it comes from a sample. And we're going to see the formula right here. So the formula right here is the standard error of P hat is equal to, and very similar, P hat times Q hat over N squared root. And you probably remember from last module, I was saying P times Q over N squared root. Now we have to keep those two separate in our minds. P times Q over n square root, as we saw previously here, is the standard deviation for the sampling distribution of P hat. P hat times Q hat over n square root is the standard error of P hat. And so it's very similar. And you actually will not have a P. Because think about this. If we go out and talk to people about who they'll vote for, we only have our understanding from the sample. We don't know the truth. I mean, we will eventually when the election comes around. But at this point, we're trying to estimate the truth, and we're getting this information to estimate it from the sample. You cannot, for these problems, reverse it because you don't have a P to put in there. It could technically say, is 50%, which would be good enough to win the election, not by electoral college rules, but is 50% in the interval. And if we're giving a value to estimate, that would not be P. So be careful, because I have seen people get this wrong. But in this example right here, we have in this equation P hat, which is the sample proportion, Q hat, which is the complement of the sample proportion, and N, which is the sample size. So it just changes a little bit. So let's talk about a recent poll right here. 24% responded they were suspicious of performance-enhancing drug use among swimmers who break world records. Is the proportion of all U.S. adults who are suspicious close to 24%? So let's build a confidence interval. This is what we talked about before, where we said, okay, I'll be there at 4 plus or minus 10 minutes. Now, how are we going to build this? Well, this goes back to what we've seen before. We've seen the empirical rule. We have 68% inside of 1 standard error this time, 95 inside of 2 standard errors, 99.7 inside of 3 standard errors. This is identical to what we've been doing. A lot of times, we'll use 2 standard errors. Now, the truth of the matter is that 1.96, and I'll type it in the calculator window, 1.96 is a true 95% confidence interval with z-scores. We've lied to you this whole time. A 2 standard error confidence interval is 95 point, whoops, I hit a wrong button right there. 95.449, I believe. And if you notice, if that's where 2 is at, we have to bring it in a little bit. We need to have less area covered. But a lot of times in practice, people will use 2. It's very close to what we can use of 1.96, which is the truth. And there's always more decimals after that. 1.96 is very good, but you could go more decimals after that. So here we go. Here's our 95% confidence interval, and it's more true if we use 1.96, but 2 is often good enough and used for quick calculations. If you put it into software, it will use the accurate 1.96. If you want to do it in your head at times, it's very quick and easy to use 2, and that's why people love it. You can just make a 95% confidence interval, and boom. Now, what does this mean, this little crazy guy up here with his Acme trap? Well, he's trying to figure out where the true proportion is. He believes, he's 95% confident that the true proportion is contained in this interval. That means when I go out and sample right here at this P hat, this is the sample proportion I observed. Now I'm going out 2 standard errors, and I'm saying I am 95% confident that the true proportion of people who will vote for Obama in the US is contained in the interval, and now it's in my lowest to my highest. That's all we're doing right here. We're finding a sample standard deviation from going out and talking to people, and then we are using that to estimate the true proportion. See, it says captured to capture P. I like how it says guaranteed, because we're only 95% confident in this. It's not guaranteed. There's no such thing as 100% confidence interval. You would have to say Obama will get 0 to 100% of the vote. As you can tell, the confidence intervals get wider as we get more confident in them. So what does a 95% confidence interval really mean? It means we're 95% confident that the true proportion will be contained in the interval, and that should happen 95% of the time. A lot of 95% in there. Specifically, this graphic hits it home, because this is the true proportion, this green line right here. The green line is not in all the intervals. It's not in this one. I might miss one. There's one interval it's not in. It's not in this one. And it's not in this one. That is 3 intervals. And I believe that is all that is on the side. So there's 3 intervals that the true proportion is not contained in. Out of 20, the true proportion is only contained in 85% of the intervals. But if we did this more and more and more and created more intervals and did it all properly, we'll talk about the assumptions in a moment. If we did it properly, 95% of 95% confidence intervals should contain the true proportion. And when I slow down and speak, that's a very important thing right there. 95% of 95% confidence intervals will contain the true proportion. And this is given the assumptions are met, but it's kind of the law of large numbers happening again. You see here on the first one, we have 0% contain the true proportion, and then 50% if I'm just going 0 out of 1, 1 out of 2, 2 out of 3. It's going to approach the truth of 95% containing the true proportion as we make more confidence intervals. So we won't always see the true proportion inside of it. It's just that 95% of 95% confidence intervals contain the true proportion. And we could say that about anything. We could say that about an 80% confidence interval. 80% of 80% confidence intervals will contain the true proportion, as it says right here. And it's a little more broad in terms right here. We are talking about true proportions in this module, but the true parameter, because we are talking about the population proportion, which is a parameter. So we're looking for the true parameter, and in this module, we are talking about the true proportion. So it works for anything. If you say, this is for a later module, we expect 95% of all 95% confidence intervals to contain the true mean. So it could work for anything, true standard deviation, whatever you're trying to estimate. So let's look at how we construct it. This slide is very important right here because we're looking at the formula for once. The formula is not that complicated. You've already been doing it. Think about it. You said you would arrive at 4 plus or minus 10 minutes. That's your formula. This part right here is your best estimate. I want to make this very clear, and this is great notes to take right here. This p hat right here is your best estimate. It comes from your sample. This is, for example, the people who said they'd vote for Obama. Or in the above example, it is for the swimmers. This is the sample proportion who said they're suspicious. So our best estimate is 24%. If you were to tell me you'd arrive at 4 and that's your best estimate, I'd put that at my center of my interval. That's where I really think you're going to land. Then I need a margin of error. So here's the margin of error right here. This, everything after the plus or minus, I will make this clear. Everything after the plus or minus is the margin of error. Right down here, this same formula, everything after the plus or minus. You told me 4 plus or minus 10 minutes. So we have a center of the interval and a margin of error. So looking at this right here, we can say that we are 95% confident the true proportion of people in the US who are suspicious of swimmers using drug enhancers to break records would be 21.3% to 26.7%. So specifically to say it again, I am 95% confident the true proportion of people who are suspicious of swimmers is contained in the interval 21.3 to 26.7%. And everything says the same here on the slide. We're using this to estimate the truth. I want to make that very clear. Does our interval contain p? The answer is we don't know. We are 95% confident that it contains p. Specifically, we are not 95% confident p falls in the interval. P is something that actually exists. P is the true proportion of people who are suspicious of US swimmers. But in truth, there's a real proportion out there. So our interval is what is being created. Our interval is the active thing. When we go out and sample, we could get different samples. So our interval might contain it. It's not that p falls inside of it because p is out there not moving. Our intervals are being created every time we make a new data set. Every time we have a new data set, we get a new interval. So our interval might contain it. It's a thing that we like to be specific on the wording about. Now, when it comes to making our confidence interval, we can choose just how wide it is. Now, think about this, though. If I tell you I'm 99.99999% confident that I'll arrive to class at some point, the teacher might not be happy about that. You're telling me at some point you will come to class. That means I could walk in during the last second and leave. But if I tell you I'm 95% confident I'll show up during the first 5 minutes of class, what? That sounds a lot better. Because you're telling me that you're really sure that you'll be there within the first 5 minutes. And specifically speaking, that interval would be 2.5 plus or minus 2.5, because I'm going to be there at the start or I'm going to be there once class has elapsed 5 minutes. So with this in mind, sometimes we want to build a tight confidence interval or a really wide confidence interval, but we have choices. Let's look at our 99.7 confidence interval. Wait a minute here. We've done this. We've seen this. We've seen this with a empirical rule, 68, 95, 99.7. And if you look along this number line right here, if we go to 68 and then to 95, 90 would be in between here because 68, 95. So 90 needs to be in here. 95, 99.7. So 98 is in between here, in between 2 and 3. And I don't say -2 or -3 because it will go negative and positive. If we have to go up to +3 and go down to -3, that's why we do the plus or minus. Each one of these from P right here, P hat, all the way to P hat plus 3 standard errors is just going up 3 standard errors. P hat down to P hat minus 3 standard errors is down 3 standard errors. So the whole length of the interval is 6 standard errors. Once again, we say that the length of the interval is 2 times the margin of error, or the margin of error is half the length of the interval. And we're really giving up a lot here because this can make your interval very wide. So you have to be careful sometimes. You have to pick your confidence interval and how wide you want it to be. And these are our most common. The most common ones are 90%, and I'll write in the numbers for that, and you'll watch it happen right here. 90% is 1.645. That makes a 90% confidence interval. 95% is 1.96 to be exact. And 99 is 2.5758. And these are all just carried out to a certain degree of decimals, but there's even more. And you could probably guess a 99.7 is basically 3. This is what we're seeing before, 99.7% confidence interval. Could you tell me what a 68% confidence interval would be? A 68% confidence interval would just be 1. So you can test this out with the David M. Lane applet and get a little practice. You don't need to know these numbers, and your TI calculator will do it for you. So when it comes down to it, we have what are called the critical values, and I've just been mentioning a few. We oftentimes use 2 for the 95% because of the empirical rule. Now, as I keep saying, the exact is 1.96. Calculators and oftentimes on tests, we will give you these numbers, such as z is equal to this, or later, t is equal to this. So this is what we call the critical value, and this is part of the margin of error. This 2 right here is actually z. So I want to make it very clear, in your formula that you've already been looking at, p hat plus or minus, this is now z times the standard error of p hat. Where does it come from? As I was saying, the David M. Lane applet. 90% confidence interval is 1.645. And you can click on the second button here in the applet and put in any number for area and make sure you go to between, because this looks just like our Acme picture from before. 0 up to that value, 0 down to that value. What was at the center here? P hat. And we are trying to say we are 90% confident that P is contained in this interval. Very specific. 99% confidence interval is really wide. And look at this. Wait, what did we say for a 3 standard errors? 99.7. Oh, excuse me there. 99.7. That was for 3 standard errors. And look at the z-score for 99.9. It's even wider. We're literally just covering more and more area every time we go out more. So if we were to do a 99.99% confidence interval, it would go out even wider and the z-score would be even bigger. And think about the way this works in the formula. In the formula, if we change this number, the margin of error gets bigger. When you go from 95 to 99.7%, your margin of error goes from basically 2 to 3, making the interval wider. Hence, you're more confident. So we've seen these assumptions and conditions before. We have that the sample size must be large enough that the central limit theorem applies. And we're going to speak specifically what we mean by that. We have that they must be independent of each other. Now, these aren't the conditions we want you to memorize. The conditions will be the randomization condition, which goes to them being independent and everything great there. So if we collect our data randomly, we're good. We need to go out. We can't talk to the first 100 people we see. We have to do simple random sample. We have to do stratified sampling. We have to find some way that the people are randomly selected. 10% condition. Once again, this relates to the math and how error is compounded by us sampling more than 10%. Going out and doing this is not the end of the world. This is a condition that we should know. If we sample 11%, everything doesn't fall apart, but we would still have problems that we would not want. It's not like 9% is great and 11% is bad. Don't sample more than 10%. So once again, if you have 30,000 people at UT, don't sample more than 3,000. That's how you do not violate that condition. The success failure condition is specifically what we were talking about when we mentioned the central limit theorem. So we need it to look normal. We need the data to be normal enough that we can use these z-scores and empirical rules with them. So what we need here is not NP greater than or equal to 10, NQ greater than or equal to 10. We don't know P, we don't know Q. So we need the sample size times the sample proportion to be greater than or equal to 10. The sample size times the complement of the sample proportion to be greater than or equal to 10. So this means if I go out and I talk to people about them voting for Obama, I need at least 10 people to say yes and at least 10 people to say no in my sample. Very specifically right here, these relate to how many people say yes or no in your sample. So when the conditions are met, we have that we can use these normal methods right here because this formula is based on the normal method. And I just want to pause here for a moment because this is the real understanding. This is everything we've come to in this chapter, is being able to use this formula of the sample proportion times the critical value obtained from the David M. Lane applet or memorization times the standard error of p hat, which is p hat times q hat over n square root. So we can pick, this z has a star because we can pick it. We can make it whatever we want. If I make it 1, I'm making a 68% confidence roll. If I make it 2, I'm making basically a 95% confidence roll. If I make it 99%, or excuse me, yeah, if I want a 99% confidence roll, well then it's 2.5758. So I can pick the z and then I have to find the appropriate level for it. So let's look at this company right here. A company just made 1 million rewritable CDs. We will ship them if we are reasonably sure that less than 2% of them are defective. We take a sample of 1,500 of them and test them. 22 are found to be defective. So let's calculate the sample proportion defective. We have 22, oops, we had a extra thing in there, 22 divided by 1,500, there we go. 22 divided by 1,500, with this in mind right here, well, we're good to go, right? We're fine. We don't know for certain yet. We have 1.46% defective in our sample. With this in mind, let's look at our conditions. Do we have more than 10 successes and 10 failures? Yes, the successes right here would be 22. The failures would be right there. It's literally the number of successes and the number of failures in the sample. Both are greater than 10. Did they randomly sample them? Yes. Is this less than 10%? Yes, they sampled less than 100,000 of their CDs because 10% of a million is 100,000. We pass all the conditions right here. Good to go. Always check this through right here. So creating our 99% confidence interval, what would we get? And there is, it's actually rounded on the slide, it's 2.5758 if you carry out a few more decimals. With this in mind right here, let's calculate the standard error. The standard error is 0.014666. And let's copy and paste it. I need to find P, and I'm going to show you the formula while we do this. So try this for yourself if you want. We need to take 1 minus, and what have I calculated here? I am calculating Q. That is Q right there because it's 1 minus P hat. So Q hat is 1 minus P hat. And then I'm going to times it by P hat. Then I'm going to divide it by our sample of 1,500. I'm just doing the formula right here. So P hat times Q hat over N, and then square root. So 0.003103. Let's copy this, and let's bring it back over here. We know that we need to go 2.5758 away from the sample proportion. So let's times it by 2.5758, and that gets us basically 0.008. If you remember properly, our confidence, the center of our confidence interval was, and that's our sample proportion right there. So let's subtract our interval goes down to about 0.6%. So somewhere between 0.6 to let's add 2.26, or excuse me, yes, 0.6 to 2.26. That's not going to work for us because we could get complaints. We might have over 2%. We wanted to know if we can say that less than 2%, and we wanted to be really confident. We are reasonably sure that less than 2% of them are defective. Well, our interval goes from 0.6 to 2.26. So that's not going to fly. We can't ship these CDs. So if we had done it as a 95% confidence interval, how would this have changed it? Let's just think for a second. We have here, let's delete this out. I believe we still have the standard error in. Well, let's divide it and we can get the standard error back. So there's the standard error now. And if we had times this by 1.96, we'd get 0.61. So let's take this right here, plus 0.00, and then 61. Still, if we had done it with a 95% confidence interval, we would go over. So we're really not going to be able to ship these CDs. If you notice here, the upper portion of our confidence interval, it could be true that the true proportion of defective CDs are 2.07%, and that's going to cause complaints, and that's going to cause problems. So both of these contain 2, and that's not good. That means 2 is possible. And if you also notice, this interval right here did not go nearly as high. I didn't calculate the lower bound because that's not really what's in question. This interval did not go nearly as high as the other one. And as you can see, when we do this, this goes further out right here. A 99% confidence interval goes further out than, let's look back here, a 90% confidence interval. It doesn't go as far out as a 99. There's a 99% confidence interval. There's a 90% confidence interval. If you notice, we're just shading out from the center. There's a 99% confidence interval. 99% of the area under this curve is shaded, and it goes out from the center. It's symmetric. So we cannot make this decision. Once again, if 2% is in the interval, we can't say at less than 2%. We're not confident enough in this. So when we look at the margin of error in the news, we see this all the time, especially in Gallup polls. They have many ways of doing it, so I'm not going to prolong this much longer, but we see this all the time. They go out and they talk to people about every single issue, and they always use a plus or minus. And there are certain ways that certain polls like to do this. They might estimate it using a p-hat equal of 0.5 when they do the standard error. Lots of different ways. They might use a margin of error of 2 at all times, basically making a 95% confidence interval. But this is some of the ways that polls do it, and we see confidence intervals at all times. Once again, email me if you have any questions.